taking the matrix A that you see here, we multiply that matrix by the x vector, which has x1, x2, and x3 as components, and x is a column vector, so that we can multiply it by the matrix A. So we do AX, and people had some uncertainty doing this, but if you understand matrix multiplication, you understand that A times the x vector looks like this. Here's A, here's the x vector, okay? And we also note that the x vector was indicated on paper as x in a typewritten file is x1 semicolon x2 semicolon x3. And that could also be written as x1 comma x2 comma x3 apostrophe, the apostrophe indicating the transpose where the rows become columns. So if this row becomes a column, that's what you get. If the semicolons delineate rows, so this is a row, this is a row, this is a row, well, there's a row, there's a row, there's a row. That's what the notation tells you. You might see this notation, you might see this notation. I can't easily render this in anything that'll work across platforms and still be editable. So the problem tells you to do this. So you do this and you write this. Now when you have this written out, well, it should be obvious what you do. You multiply the 103 row by the x1, x2, x3 column. First times first, second times second, third times third, and you add them. So you get 1x1 added to 0x2 added to 3x3. Some people are still not multiplying their matrices correctly, so you really want to correct that. Once you get in the habit, you see how it works. Okay, then you have 0, 2, 4 multiplied by this. Well, 0 times x1, 2 times x2, 4 times x3, there it is, and you add them. And here you get 1 times x1, 1 times x2, 0 times x3. The first row times the column goes in the first row. Second row times the column goes in the second row. Third goes in the third row. Now you don't then suddenly just put commas between these things that are added. You add them, okay? And some people are putting commas here because there's a little confusion, and matrix multiplication takes a little getting used to, but you want to certainly get used to that, okay? So you add these. So x1 plus 0 plus 3x3 is just x1 plus 3x3. Okay, you don't bother writing the 0. So you're going to get from this one 2x2 plus 4x3, from this one x1 plus x2, and that's the product AX. Now, if you had an equation like AX equals A times the x vector, and I put arrows incidentally over this x vector. Now, on your paper, that's going to be bold-faced. I'm not going to put an arrow over it, I'm going to bold-face it. So if it's bold-faced, it's a vector, and usually a column vector. We got some background music, I hope you enjoy that. Okay. Now here, then, our matrix equation AX equals B, well, this is AX. This would equal some B vector. In order to be equal, of course, the B vector would have to have 3 columns, okay? And it would have to be a vector, it would have 3 rows. It would have a single column and 3 rows so as to be compatible with this. If it doesn't have a single column and 3 rows, it can't be equal to this because this does. 2 matrices are equal if and only if they have the same number of rows and the same number of columns. Okay, well, this equation can be solved by multiplying both sides by the inverse matrix. The inverse matrix is the matrix which, when multiplied by the original matrix, gives you the identity matrix, and the identity matrix is an identity. The identity times the x vector is just the x vector. So A inverse times A gives you the identity. The identity times the x vector is just the x vector. And of course, you do A inverse on both sides, so the x vector will be A inverse times B, the B vector. Now, how do we find an inverse matrix? Okay, well, it's a little bit complex, but it involves operations that you're perfectly capable of doing and that you know how to do if you know how to reduce a matrix, because all we do is we take the A matrix and put it here, and we take the identity matrix of the same dimension and put it here. So we augment the A matrix with the identity matrix. And then we row reduce this big matrix until we end up with the identity matrix here, because of course in the row reduction process we will ultimately end up with the identity matrix unless this matrix doesn't reduce to the identity. Remember, this matrix, okay, the identity matrix is this. This matrix will in many cases reduce to this matrix. If it doesn't reduce to this matrix, that means you're going to have a row of zeros, okay? And if you get a row of zeros over here, you can't reduce the A matrix to the identity matrix, and that means that the matrix doesn't have an inverse. Because what you get when you've reduced this matrix to the identity, and of course you're doing the same operations to the whole row, you're going to end up with the identity matrix here and the inverse matrix here. So what you get here will be the inverse matrix. You reduce this matrix to the identity, and you take whatever you get over here, and that's your inverse matrix. Now, I'll go through that process for these matrices, but that's the process. Once you get the inverse matrix, you can multiply it by whatever your B matrix is here and get the X, which when multiplied by the A matrix gives you B.